Let's start. So my name is Konstantin Kosinsky. I'm with Azure DevOps team at Microsoft. Especially, I'm working on analytics service. I joined Microsoft about 7 years ago. Before joining, I was SQL Server Data Platform MVP. When I joined, they took it back, so it's a bit sad. So here's my contacts and the event presentation. We will share this presentation afterwards. So if you have any question, you can contact me. So what are we talking today? This session will be about Columnstore indexes. I will explain what I'm doing, like what is an analytics service that I'm working on, just a context. Then we will talk about some internals, and then I will go through about 8 different lessons that I learned when building the system. Okay, so what is Azure DevOps Service? It's a reporting part of Azure DevOps platform. It's available on-prem as a TFI, Team Foundation server, or in hosted. As a reporting platform, we allow almost all data that's available in Azure DevOps to build some visualization reports, stuff like that. So it means we have data about pipelines, CI/CD, continuous integration, continuous development. So it's your releases and your builds. It's work item tracking, your stories, bugs, tasks, epics, and stuff like that. It's manual automated test. And now we are working on adding a code data, and it can be both. It will be Azure repos. And it will be GitHub. So we have two sources for Git data. In the future, we can maybe add Bitbucket or other sources. So from endpoint of user endpoint, analytics service gives a bunch of widgets that give you insights inside like your work item tracking, for example, which this screenshot shows your velocity, how it burning and up or down, your feature lead cycle time. It provides insights into how healthy and fast your pipeline, like pass rate, execution time, number of tests failed, and you can dig deeper and find other information. So if you are using Power BI, we do have extension for Power BI. So you just open Power BI and go to Azure DevOps or Azure DevOps server, aka TFS, and you can connect and load your work item tracking data. In addition to this scanned reports, we allow people, and basically we're using it ourselves for building everything. You can query us with OData. So think about OData as something very SQL-like over HTTP. Here's a sample. I can ask for work items. Like for bugs. For example, I interested in the top 10. I interested in ID, title, and type. I can go and expand any navigations. In this case, I'm expanding like who is assigned to, and I ask extra filters. I want, for example, here I ask for only work items that belongs to my team that's created after a particular date. So, and you get some JSON objects that you can parse and a lot of tools that already know how to deal with data outputs. The biggest part is we use aggregation extensions, and aggregation extensions allow users to do ad hoc aggregated queries. So they don't. If I want to build your velocity, you don't need to load all data to client side, do some transformation. You can ask just aggregation. In this example, I ask for test runs from particular build since particular date, and then do aggregations by date and number of past tests and failed test and stuff like that, and I get JSON object. So it's how service works, it's what is visible from users. When we start building the service, we had a bunch of requirements for our query engine that we had to satisfy. First, it had to deal with a huge amount of data. For example, one of our biggest account in terms of amount of test results is .NET Core. They on good day can produce up to 500 million test results. It's a lot of data. And we not just have a lot of data, almost in every single query touches big chunk of this data. You not like have a billions of records and extracting one. You asking for millions of records and aggregating them. And because we are reporting solution, we do not know what people going to ask us. So we need to support arbitrary filtering, aggregation, and group buys. And some data types are just insert only, like test results, but some can change. So we need update and delete to be to be supported. We need close to real-time ingestion, and data should be available all the time. So I couldn't afford technologies that require like nightly rebuild, because as soon as you modify work item in a couple seconds, I want to see chart change because it was modified. We couldn't be 100% cloud only, because we have Team Foundation server and our service have to run as part of Team Foundation server on-prem, so we need on-prem support. We need even we can deal with a lot of data. For most cases, we need very very high performance of sub-second. People will not wait for widgets to render if they need 10 seconds or 10 minutes to render. All database maintenance had to be online operations, and it should be reasonably priced. So it means I couldn't give every customer a 30 nodes Spark cluster, because it will be very expensive for me. When we started working on the service about 4 years ago, Columnstore looked like good answer. So doc says it provides great data compression. It's designed for performant database warehousing queries. You don't need to index your tables for each column, because we don't know to support arbitrary filters. And starting with 2014 version of Columnstore indexes in SQL Server, you can support trickle updates and inserts. So let's look how Columnstore indexes really implement all this good performance for big amount of data. So imagine I have a table with 6 columns, and this table has 3 million records. In this case, data will be stored in something called row groups, each about 1 million records in size. And in my diagram here, like orange is one row group, red is another row group, and again orange again is one more row group. And for each column in each row group, it's compressed separately and called segment. So this blue rectangle is one segment, and inside this segment, it's only one column. So a lot of data are kind of it's the same values repeated multiple times. So Columnstore indexes do great compression. For example, if you have like string values, and it's like bunch of A's, then bunch of B's, then again few A's and few C's and something like that. What Columnstore indexes will do, first it will build dictionary to keep only integers instead of full strings, and then it will say if I have 15 A's, it will keep 50. A was repeated 15 times. Then it's few times B, stuff like that. So as a result, if you have a million records and only 100 of unique values, it will be pretty good compression. So then I want to query it. So for example, I want to ask, give me a sum for column C1 and C2 for my table. This query does not touch column C3 and C6. What will happen? Segment elimination won't happen. SQL Server will not even try to read data from these extra columns, because each column stored separately, we can give good performance, like just keep a lot of data. Another case, let's assume I have a query when I have extra filter. For each segment, in each row group, some metadata is stored, and it's a min max. And in my case, for column C4, I have that first row group values will be from 1 to 10, in second from 11 to 20, and so on. In this case, I could eliminate not only columns that I'm not touching, but row groups they're not touching. And this min-max comparison really fast, so I don't need to read all this data. So what come like internally? What five? So it's basically five pillars that store indexes stand on. First is segment elimination. I explained this. Don't look on row groups or columns that not in query. Second is a predicate pushdown. Instead of taking a column, so like segment with 1,000,000 rows, unpacking this to 1,000,000 like real rows and iterating one by one, SQL Server is able to do this operation on compressed data. So if my query says give me when column X equal B, and I have it's already compared like 15 unique values, I just look on this dictionary and eliminate everything. We'll basically do 15 comparison instead of million. That kind of good performance improvement. Second one, third one is local aggregation or aggregation pushdown. Again, if I want to sum values and they're already in a dictionary form, I don't need to do sum value million times. I sum how many, like multiple for each unique dictionary value, I multiply by how many records is and just sum this. So as a result, again, million sum operation converts in few hundreds of multiplication sums. Yes.
You're saying compression. Which
Yes.
type of compression? Is it page? Is it what else? There page or row?
No, so it's completely different from compression that you have for all store. So idea of compression is you have first you have one column and you need to compress records from this column. So what SQL will do? First, imagine you have a values like 1,000, 15,000, 17 and stuff like that. So basically you need 2 bytes to store that. But if you calculate a base like it's 1,000 plus some small shift, so now you have 15 and 17 plus shift, so you already use 1 byte. Another trick, because value are repeating itself, it's doing like says, oh, I have 15 tens store. Instead of 10, 10, 10, 10, 15 times, it says 10, 15 times. Then it's 700 times. So instead of repeating 700 times, how it will be done in row store, it will be like 700 times and stuff like that.
Sounds like a data compression that you can have in SQL Server.
Yes.
Because it basically removes the, it only keeps the unique values and it probably removes everything else.
Yes.
So do you need for Columnstore, do you need a data compression or it's a built-in compression?
It's separate one. So like row and page is using different algorithms, and in Columnstore it's like much more algorithm, and because they work on only single column for each segment, it can give you much better compression.
Got it. What happens if, so let's say you have an index on the column and you adding a Columnstore index on the same column? There's any conflict there?
So Columnstore can be in two shapes: clustered Columnstore index and non-clustered Columnstore index. So if it's clustered, all columns are in clustered index. For non-clustered, it's only selected columns. You can build non-clustered Columnstore like non-clustered index on top of clustered Columnstore index, but B3 on top of clustered Columnstore index.
Yes. So let's say you have a non-clustered column on, let's say, index in on a column, let's say total, and you're adding a Columnstore index on the same column. Is that
yes?
There.
It will be two separate indexes, and optimizer will decide which is better for you.
So there's no conflict.
No conflicts.
Okay, cool.
And in after compression, so it's one interesting feature called batch mode. So originally batch mode is how SQL Server executes your query. So if you usually look on a plan in a SSMS, you will see you have operators with arrows. how this stuff works. Operator opens and asks, give me a next row from previous operator, and previous operator go for upstream and ask, give me one row, give me one row. So as a result, when you in row mode, you need to go, if you need to iterate through million rows, you need to like basically loop that does million iterations. What batch mode doing? It deals with the batches of rows, about 900 rows in the one batch, and this batch should feed into 64 kilobyte. Why 64 kilobyte? Because it's a size of L1 cache on modern CPUs. As a result, when you operate with one batch, SQL can fit in CPU cache and do like less memory misses and stuff like that. And one more interesting feature about batch mode, it uses SIMD. SIMD is a single instruction, multiple data. It's a feature of modern CPUs when you can, instead of, for example, you have array of integers or doubles, and you can ask CPU, say, give me a sum of these doubles as a one CPU instruction instead of like sum plus 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 plus. So batch mode on CPUs that support this allows you to like leverage your power of the similar instructions to give even more performance. In next slides, I will mostly talk about first four, and just batch mode is given for Columnstore indexes. With 2019 of version of SQL Server, you will be able to have a batch mode for row store. Now, it's allow you to improve performance when even you have row store and your query still looks like aggregation one. Okay, so I was advertising how awesome is aggregate local aggregation or aggregate pushdown. Trick is not all data types supported. So I have a table, and this table contains about 30 million rows, and I want to sum all these 30 million rows, and now let's just sum for particular column. Here's the plan and execution time. So I keep my duration second as a decimal 18,3, and I execute this query. It uses this Columnstore index, and execution time is 15 milliseconds on and it uses 4 cores. So 30 million rows, 15 milliseconds. Sounds like a good performance. But if I make this column not decimal 18,3, but float, I will still have a good performance. It will be sub-second performance, but it will be about 55 times slower. Why? Because in first case, decimal 18, comma whatever, allow you to push down to aggregation and basically deal with this compressed form, very optimized for summing. And in case of float, SQL Server will need to extract the row group, unpack it in rows, and just do million comparison. How we can notice that Columnstore local pushdown, aggregation pushdown happened? In first case, you see this is very narrow arrow between scan and hash aggregate. In second one, is not that narrow. If I look in details of second operator, I will see in first case, I will see actual number of locally aggregated rows, 29 million. So all calculation basically happened on a few, on a dictionary of unique duration seconds. And it's give us 55x performance improvement. So as a result, when you're designing your tables for Columnstore indexes, and in my slide, it's a note, it's a link for documentation that says which column support aggregation pushdown, which is not. Rule of thumb, all integer column supports, decimal up to 18 supports, and everything else does not. Okay, second trick.
So basically, the smaller it is, the bigger chances to be optimized for that?
Sorry, so smaller data type?
Yeah.
Yeah. So yes. So it's more. It's basically a hard limit. This data type support this optimization. This does not. That's it.
Got it.
Okay. Second trick. I was talking about compression. So let's see how compression is. And for compression is cardinality of each column really matters. I have a table with the test results, and it has a column completed date that stores about 1 billion records, and data type for this column is datetime offset. If you look on this only on this column, and because Columnstore store by column, so I can look on one particular column, it will be about 6 GB. Datetime offset is give you precision about 100 nanoseconds. So if I cut to seconds, just cut to seconds, it will be 3 times better compression. So you basically will use 2 bytes per data time offset per value. To be clear, I use this data offset 0 to just be strict that I cannot have value more precise in 1 second. But if you still use data offset and cut by second by other means, you will have the same number. So it's not data type, it's a data. But in most cases, when you deal with Columnstore indexes, you're not looking for each second. You're looking for like whole day, and you will aggregate for whole day. So if I store the same value as an integer, just date in integer form, or as a date type for the same 1 billion record, my storage size will be 900 kilobyte, and it's not a typo in my deck. It's really 900 kilobytes. So I get in like 2,500 times improvements. Why? Because I do not have so many unique values for dates. So how many unique days I can have in a year? 365. It gives me that awesome compression. And what is beautiful about Columnstore indexes, if you can have both. You can have a exact date with up to second, and you can have another column that keep only date. And queries that need only dates, they will use a small 1 megabyte column, and queries that need more, they will get more. So how I get this estimation? You have Columnstore segments DMV that gives you exact size for each segment on a disk. You just sum on it. Okay.
Konstantin?
Yep.
Quick question for you. What happens if you do a conversion? So let's say your original column is float, but in your query, for some reason, you decided to convert it to, let's say, decimal. Would Columnstore work?
Columnstore will work in terms query will be executed, but it will no aggregate pushdown because it's not compressed. So it will unpack your float, and then it potentially will be a bit faster because batch mode can kick and do some compression on the fly, but you will still need to iterate 1 million records. So it's for each segment. So it's not that one. So finally matters not only for storage size, but for aggregation pushdown. Imagine you have a query that does group by plus something. In this case, you can get aggregation pushdown too. Let's assume I have a 3 million rows, and I have 3 row groups, and I do have some column that I want to group by, and for first segment I have 16,000 unique values, for second 17,000, and for third 16,000. I try to just sum by something else, group by this column. Your details will be really confusing. I have 3 million rows. Actual number of rows is 1 million. Actual number of rows locally aggregated is 2 million. How I can translate this? If you deal with Columnstore, to number of rows that really pass through a system is the sum of this. It's 1 million rows was not aggregated. It's our second row group because it's more than some threshold that theoretically about 16,000 unique values, and first and third was locally aggregated because they have less than this threshold. So you have, and now is interesting part. You have performance gain on some row groups, and you don't have this performance gain on other row groups. But it's how it works. Actually, it's not only one case when it can be group by can be pushed down or not. Here's the link to awesome blog post from Paul White about other cases, and he shows really detailed which type, like which compression types, which data shapes lead you to have or do not to have or not have aggregation push down. And I really recommend this look in this article. Okay, so lesson number 3, predicate push down. So in addition to aggregating on storage, I can do push down my predicates. And trick is you have compressed data and you can just iterate in this dictionary on unique values and do filtering here. But not all predicates allow you to do this. For example, you have column A equals something, or column B equals something. You will have no push down because SQL needs to get column A, column B, and find all possible combinations how they overlap. If you compare column A to column B, no push down because again, two columns have to be collide. But if you have column A equals something or condition column A and condition column B, you will have push down. SQL can do push down for A, push down on B, get filtered sets, overlap them. You have push down, like predicate push down. So how you can optimize your model, your tables to support, to encourage this behavior? If you have a cases when people usually going to ask like, give me all columns that column A greater than column B. Just create a column that will already have this as a predicate, like pre-calculated this value, and teach people to use this calculated column instead of expression, and you will get much better performance. And again, each column stored separately, so queries that will touch this combined logic will be benefiting from this. Other queries will just skip this. Trick about strings. No push down on strings before SQL Server 2016, and it's still some limitation in terms of how many unique values in strings to have on the after which you don't have a push down. If you have a problem with push down for strings, try to replace the string with numbers. Like create a dimension table, push strings in this dimension table, reference with integer numbers, and SQL will give you string push down in this case.
Konstantin?
Yes.
What about cases of implicit conversion? Would the predicates push down work?
Yes. In most cases, yes. So it's some tricky cases. I don't recall now when I saw that it's affected push down, but like push downs is execution time operation. It's not like a compile plan operation. So SQL during execution says, oh, it's just integers. And you want to like sum them as a big integers. Okay, I'll sum them as a big integers as integers, but keep in mind like overflows and do this stuff. So to summarize, explicit conversions is not that big problem as for other cases.
Okay, what about blobs?
Blobs?
Yep.
So before SQL Server 2017, blob types wasn't supported. 2017 supports blob types, but I do not have hands-on experience on blob types. So in Columnstore, so I cannot say like something good or bad about this.
Okay, fair enough. Thank you.
Okay, So strings are tricky. So I told about awesome feature segment elimination. Unfortunately, so far, segment elimination works only for numeric or datetime. So if you want to filter by string, it will be no segment elimination for you. So the same for GUIDs. So the GUIDs and strings on the same level. In most cases, it's not a problem. Imagine a work item table, and work item can have a column type. Work item type, it can be bug, task, user story, feature, and something like that. And I want to filter by work item type. I think I will have bugs in all, like spread across all tables. So even if I will have this feature, it will not give me, because all row groups will still contain records for a bug. So honestly, in most cases, it's not a problem. But if it's a problem, again, the same approach as from previous slide, replace them with numbers, create a dimension, like separate table, and let SQL use numeric codes. Good part is that in SQL, SQL have a feature called SQL Azure SQL Database Warehouse, SQL DW. That is multiple massive parallel processing warehouse that is basically built on top of SQL plus some stuff, and it shares some part of source code, like implementation with a regular SQL Server, SQL Azure DB, and they already have the segment elimination on strings. Unfortunately, this feature is not enabled for SQL on-prem or SQL Azure DB. Okay, so when I showed segment elimination, I showed this nice column C4 that had a very aligned min and max. So I said my first row group for column C4 was from 1 to 10, second one from 11 to 20, and stuff like that. It happens when you insert data in the order that you're going to query. And here's a sample. I have a table, and it's for each segment, I have a min and max. And if you look here, you will see from first line, it ends with like 82 or 7, and next start with 82 or 8, then 230, 231. So in this case, it's no overlaps between segments. It's awesome case as it was in my original diagram. So if you, for that table, you will filter by some value, even you have hundreds of thousand segments and tens of billions records, it will like look for one segment to get data. You have very fast query. But if you look on more real life data, here is the case. So I have a column, and my segment 20 is for September 6 to September 8, and 21 from September 8 for September 9. So in this case, if I ask for data from September 8, I need to read 2 segments, because first segment have data from September 8 and second have from September 8. And here's even worse. If I ask for data from September 12, I will need to read 3 segments, because it's how data distributed. And worst case, here is the segment that contains data from August 18 to September 17. What it means? It means that every query that will need something in September will look in this segment. So as a result, when you are not getting good segment elimination, try to look on these alignments and see how this value overlaps, and maybe reorganize your table to have a better alignment. Okay, so what affects your alignment? First is its updates. So in Columnstore, update is delete plus insert. And trick is each segment, as soon as compressed, it's sealed. You cannot modify records in it. But if you want to delete records in segment, it's a special part of segment called deleted bitmap. So it says, oh, row 17,023 is deleted. So if I execute query like that to modify a few records, I will have data from the first row group for second row group. I will add deleted bitmap in a first row group and third row group, plus I create one more row group. And now if I execute the same queries that eliminated almost everything when I start talking, it cannot eliminate old row groups plus new row groups. So it's basically reading twice as much data. As a result, if you do a lot of updates, your segments start being not very aligned. You have overlaps, more segments need to be read. So more updates, worse performance. So what you can do about this? First, try to avoid updates if you can. If you cannot, try to, we will talk about deltastore in next page, but try to do updates, steal records and steal in deltastore. Second one, try to build your tables in a way that you can contain where updates happen. For example, if you have a table that have historical data plus current data, let updates happen in current data and just insert to historical record. In my case, we do have work items table, work item revisions table that splits into parts. Current state of work items, like how bugs looks like now, and all previous revisions. As a result, I do update in my current table and I only add to my historical table. So yes, I have this bad segment elimination and fragmentation in my small current table, but my historical table is perfect. Or you can do periodic index maintenance, and I will have a few slides about what you need to be aware when you do index maintenance.
Konstantin?
Yep.
Since you mentioned updates, so in the row store indexes, there is a problem of too many indexes. Basically, if you have too many indexes, it actually might slow down inserts, updates, and deletes. Is this problem exist in Columnstore? So many Columnstore indexes would actually slow down the operations.
Okay, so first, you can have only one Columnstore index on the table.
Okay.
So it can be clustered, or one clustered, or one non-clustered.
But only one.
But in some cases, if you do presence of clustered Columnstore index with a non-clustered index on B3 index on top of it, when you have too many updates, like and your shape of index like with a lot of this bitmaps, deleted bitmaps, a lot of data and deleted bitmaps, your updates could slow down. So it's one more reason to keep do maintenance and avoid and to periodically clean up these deleted bitmaps.
And I'm assuming Columnstore index has the same sort of fragmentation stats.
Yes, I will basically in a few slides I will show that.
Okay, awesome, thank you.
Okay, so I mentioned deltastore. So when I started talking about this row groups, I said row group is about 1 million. So how, if I just add one row, where it will land? It will land in deltastore. So what is deltastore? It's a regular heap table with no compression where you insert your row. So when you do insert, it goes not directly to compressed part of Columnstore index, but to deltastore. So, and as soon as your deltastore reaches 1 million records, it's compresses. So if you have less than 1 million records in your deltastore, it will not be compressed automatically. So problem with that is each query had to read whole deltastore because you look on compressed segments, but you still have something in deltastore, so you have to read whole deltastore. And deltastore could be much larger in terms of megabytes than you expect. Imagine you have a table with 100 integer columns. Each integer column is 4 bytes. 4 bytes by 100, it will be 400, and it's no compression, so nulls will still pay you, each null will still cost you 4 bytes. So now we have 400 bytes per row multiplied by 1 million rows close to this threshold, and it will be 400 megabytes. So if you have that wide table with And with big data store, you will each query need to read 400 megabytes of data. And process it. It's not very fast. So if you see that your delta stores are too big and stay big too long, you can force compression. You just do alt index reorganize with compress all row groups. In this case, it will go and compress this like forced compression of delta store. Okay, can we avoid delta store? Yes, if you use clustered Columnstore index and insert in a batches of 100,000 rows, and here's exact number, like for 100 kilo rows, SQL will write directly to Columnstore without writing to delta store. So if you do batch update, like a batch inserts your like ETL that deals with a big chunk of data, just make sure that your batch is 100,000 and you avoid writing to delta store and compressing after. But you need to keep statistics up to date, because if when plan is compiled, starts to low, SQL could say, oh, it's only 3 rows, like by estimation. I will not even try bypass delta store. So keep in mind this threshold, and that stats should be good. Unfortunately, if you have non-clustered Columnstore indexes, it's no way that you can bypass delta store when you're updating. Okay, so second question, can delta store be more than 1 million rows? Yes. Imagine you have a lot of parallel writes that writes to one table with and they need to write to delta store. In this case, SQL will put a log on whole delta store as a result, but for next thread, we'll just create new delta store. So you can have a lot of small delta store, and each will struggle to reach 1 million rows. As a result, you can have like hundreds of small delta stores with less than like few 100,000 rows. They are already big, but together they more than million, but they don't compress. So in this case, if you see this in your database, just force compression, it will compress all the small delta stores together. Another case, if tuple mover is busy. So what is tuple mover? It's a background process that basically converts delta store to compressed shape. How it works? As soon as you reach 1 million, tuple mover says, okay, stop writing to this delta store. He is in U1, write in U1. I will process old one. But by the time you finish processing this 1 million, you maybe can insert it 1.5 million in new data store. And it will not start compressing till you reach 2 million. So by the time you compress this 2 million rows, you already inserted 3. It will reach to next power of 2, 4 million, and so on, so on. So you can have up to 33 million rows in your delta store. After that, it's okay, no more inserts. I need to be done before you can insert. So keep in mind, if you insert it too fast through delta store, make sure that tuple mover it's catching up. One tricky part is physical partitioning. So if you have multi-tenant environment, you have a small tenants, big tenants, and they are next to each other. You need to keep in mind that each time when you read whole segment, you always you decided the SQL decided you need to read a segment, you read whole segment, all million rows. In this case, if all tenants in one physical partition, let's say you have a small startup with hundreds of bucks and Windows division with a couple millions of bucks, and they are next to each other, they will be compressed in few segments, and small startup will have to read whole segments for and skip all rows. So it's a kind of bad. Second, if we logs are on row group level, as soon as you do update on insert, you work in whole row group. Not good. Plus, adding more tenants in one big partition can increase your cardinality of values, so less segment elimination for you. Okay, let's give everyone a physical partition. SQL Server says no, because you cannot have more than 15,000 partitions per table. So if you need, as me, like me, 50,000, 100,000 per partitions, it will be no luck. But another problem is you have a small tenants that will never reach 1 million rows, so they will never be compressed. So for them, it's just Columnstore index will be basically table with no indexes. That is really bad. So we need to do something about. So as a result, if you have this combination, and it's what we are doing in our service, we group small tenants in one physical partition, and big tenants have dedicated partitions. So small tenants help each other to reach 1 million and be compressed and have much better performance because of that. When you have this physical partitions, you need to maintain them. So here is a view that and query in nodes that shows you how bad or good your Columnstore index is. So here it shows I have few row groups. It's the same index. Seven together. 6 of them already compressed. 1 is open. Open is deltastore. You can see a number of rows in deltastore. You can see size of rows in deltastore. So if you compare line 4 to line 3, you will see that in line 3 I have about 4 times more rows, but my size is about 7 times smaller. So 4 by 7, it's like, in this case, I'm in this table, I'm getting 30x compression. But I said more than once that it compresses when you have 1 million rows. And it's not 1 million rows here. Trick is that when you try to compress, and it's some internal threshold. If you have too many unique string values, your dictionary will be too big. So SQL need to split a row group in smaller one. So if you sum total rows from 1 to 3, you will have 1 million together, and it will be dictionary size. Then you see a number of deleted rows. This deleted rows is what number of rows mark as deleted in deleted bitmap. And your fragmentation is basically deleted rows divided by total rows. So this column fragmentation is, I just calculated this, dividing deleted rows by total rows in percentages. Okay, so what you can do about this? First, you can run alter index reorganize. In this case, SQL will look on all row groups with the deleted rows, remove these deleted rows, and try to merge different row groups together to be up to 1 million. Unfortunately, if your trim reason is dictionary size, it will not touch this row group. So if I run my alter index reorganize for this table, only segment row group 7 will be cleaned up. So 1 to 3 and 5 to 6 will stay fragmented. If you have dictionary size, still have dictionary size, but all rows are deleted, the SQL will do cleanup. Another problem with alter index reorganize is, imagine you have like pretty old row groups with some deletions, new row group with some deletions. You SQL decided to merge them together, and now you have your mean from beginning of time, max end of time. So your bad segment elimination. Okay, another option, alter index rebuild. In this case, all deleted rows will be gone. Unfortunately, SQL will not maintain order that you want. It will just, okay, I read from this table, I write to this index as fast as I can. I don't care about in which order I do this. So that can affect segment elimination. And in next slide, I will show how we solving this problem right now, but with Azure SQL database warehouse. It's still preview feature. They have an option when you create clustered Columnstore index, say order, and specify columns to order. It will be ordered, clustered columns to index, and you can have like rebuild will maintain this order. Okay, but if you now in on-prem SQL or SQL Azure DB, you need to do some custom solution. So what we are doing next. We like have a stored proc that basically reads table and writes to a temp table in orders that I want to force compression in orders that I want. So how we're doing this? I clone table structure. I copy data in affected part from my partitions I want to improve to temp table. I do it in 1 million batches to have very fast I/O because I will not go to deltastore. And its data is still available for customers. We do have a way, like in our solution, we have a way to like stop ingesting data. After we copied a bunch of data, like almost all data, we stop ingestion. We have a way for each record to say like, when it was updated or when it was inserted. So after we stop ingestion, we just do delta changes. And we stop partition. So from customer point of view, from 1 to 3, data available, everything, new data is incoming, everything is great. Between 3 and 4, all data available, but data latency start growing. So you have maybe your work items will arrive not in few seconds, but in a 30 seconds or 1 minute. And it's very fast switch partition operation that like few milliseconds and you're gone. And then you re-enable ETL so your data latency starts to stop growing. If you want to split and merge partition, you basically need to do the same, but just split and merge. And last lessons is the schema updates. Like for our service, we are online service. We could not afford maintenance window, so we need to do all our modifications online. Unfortunately, most operation with a index or column store or columns are offline. So if you just add nullable column and want to keep nulls, it's very fast. If you want to add not nullable column and set default, it will be fast too. But if you want add not nullable or nullable column and you want to set values on some crazy pattern, you need to do like add column and then you do updates. And with updates, you will update is insert plus delete, so you have 100% fragmentation. Your performance is on the floor, so your phone is ringing and stuff like that. So as a result, each time when we need to do something more complicated and add new columns, we're doing the same way as we do for servicing. We create new table, copy data with required modifications on a insert, and we switch tables. And we use the same approach to to keep low latency during maintenance, and it's visible, like just not visible for our customers. So if you want to build keep something like this, you need to build this in your update scripts. That is last slide that I have. So if you have any questions, please ask. And my contact information on the slide.
Konstantin?
Yep.
What happens if you have a column and you have a column store index on that column and you want to drop that column? Do you need to drop the index first?
I did it a couple of times. And it was about a year ago. I 95% sure that you just drop index, just drop column for clustered column store indexes. For non-clustered column store indexes, you have to drop index.
Got it. And you also said that the only way to, well, you said mostly. So in most cases, when you're trying to rebuild the column store index, this is going to be offline.
Yes. So okay. So depends on version of SQL Server. So if you on 2017 and up, you can rebuild before 2017. If you rebuild cluster column store index or B3 on top of clustered column store index, it will be a fine operation. Starting with 17, you can rebuild these indexes online, but you still it will be still a fine operation if you want to create this index. So rebuild online with 17, creation is offline.
Then you're saying offline operation. What does that mean? Is there so you still able to pull data from that column?
Like it will be like the same. Like I mean that you cannot use online equal on an index operation. So it will work table for update, at least for updates.
Got it. So this column store would not be online.
Yes.
Got it. Okay.
Yeah. More questions?
What basically would be the difference for the clustered or non-clustered column store index? Same as row store?
In some sense, yes. So like you in clustered column store index, you include all columns. Non-clustered column store index, you include only columns that you want. So if you have like big table and you want to do aggregation only on few columns, you go for an NCCI, non-clustered column store index. Another big difference, and it's basically was the reason why we decided not to stop using non-clustered column store indexes, is that you cannot bypass a deltastore with non-clustered column store indexes. So if you want to insert in big chunks, for clustered column store it will work, for non-clustered it will not. It's two differences. Oh, yeah. With 2017, you can add calculated column in non-clustered column store index, but you still cannot add calculated column to clustered column store index. So it's three differences that I aware about.
Can you have a filtered column store index?
Yes, you can have filtered non-clustered column store index. Yes, and if you remember batch mode, so it was no way to have a batch mode with if you have only row like regular row storage, but it was a trick when you created non-clustered column store index on top of it with a contradiction filter. So it's with 0 rows. It was trick in SQL to like use batch mode even for row store, but it was like a hack and trick. And with 2019, you just use row. You have batch mode on row store anyway.
Got it.
More questions? If no more questions, thank you for attending, and I hope this presentation was helpful for you. And Steve, I will send this deck for you so you can share with everyone who attended.
Konstantin, thank you very much. Guys, any questions? Guys or ladies? I guess that's all. Thank you very much. I personally learned a lot about column store index. It doesn't look so scary anymore.
Yep. And you should stop recording. I will stop, and I will stop presenting after that.
You got it. Stop recording.